3.8 centimeters per year. When you first hear that number, your brain does not register it as a threat. You think about a finger width. You think about a small piece of fruit. You think about something so modest, so harmless, so laughably small that it could not possibly matter. The moon is moving away from Earth at 3.8 centimeters per year, and every instinct in your body tells you this is fine, that this is irrelevant, that a number so small applied to a distance of 384,000 kilometers is nothing more than a rounding error in a story that will never affect anything important. That is the most dangerous mistake you could make, because 3.8 centimeters per year, stretched across deep time, stretched across billions of years of an Earth that is simultaneously slowing down and losing its most important guardian, is not small. It is a countdown, and the thing it is counting down toward is the slow unraveling of every condition that made you possible. Consider what 3.8 centimeters actually accumulates to. In 100 years, the moon moves roughly 3.5 meters farther from Earth. In 1 million years, it has moved 3.8 kilometers. In 1 billion years, nearly 4,000 kilometers. These numbers still feel manageable, still feel safely distant from catastrophe. But we are not dealing with 1 billion years in isolation. We are dealing with the entire remaining history of a planet that has already existed for 4.5 billion years. A planet whose moon has been receding since the very moment it formed. A planet whose rotation has been slowing steadily, consistently and irreversibly since the day a wandering body the size of Mars struck it and scattered the material that would become the moon into orbit. The moon is not stationary, it never was, and the distance it has already travelled is written into the rocks, the fossils and the ancient rhythms of the tides preserved in stone for anyone patient enough to read them. Here is what happens when the moon gets too far. Here is what the measured data, the orbital mechanics, the climate models, and 4.5 billion years of geological evidence tell us about a planet that is slowly and permanently losing its closest companion. The short answer is that the moon is not just a beautiful accident in Earth's sky. It is a structural component of the system that produced life, stabilized the climate, shaped the oceans, and created the conditions under which complex biology could survive, long enough to develop intelligence. When you understand what the moon actually does, the retreat of 3.8 centimeters per year stops being a trivial footnote in the astronomical record. It becomes a clock, a very slow clock, a clock that has been ticking for 4.5 billion years, and we are already deep into its final chapters. If you enjoy deep dives into the hidden machinery of the universe, the forces that shape this planet and everything on it, do me a small favour and hit the like button and subscribe. It helps this channel more than you know and allows me to keep making these long, careful explorations of the science that rarely gets the attention it deserves. Every subscriber genuinely matters. I read every comment. I appreciate every one of you who watches to the end, who shares these videos with someone they care about, who returns to this channel when you want something that takes its time with the ideas. There are people listening to this right now who have never stood outside on a clear night and really looked at the moon. Not just glanced at it, but looked at it with the understanding that what you are looking at is always in every moment moving away. Now make yourself comfortable. Let's begin. The story of the moon's recession begins not with a number, but with a catastrophe so complete that it is almost impossible to hold in the mind at once. Approximately 4.5 billion years ago, in the inner solar system of a sun that had been burning for only about 50 million years, a planet was forming. That planet was the early Earth. It had no oceans. It had no atmosphere worth breathing. It was a partially molten world, dense with iron falling toward its core, wrapped in a crust still cooling from the heat of its own formation. And it was not alone. something else was forming in roughly the same orbital zone, something that gravitational theory told us was almost inevitable given the density of material available in the early inner solar system. That something was a planet. It was approximately the size of Mars, and it was on a collision course. The object is called Theia by planetary scientists. It was roughly half the diameter of the early Earth, a fully differentiated rocky planet with its own iron core and its own silicate mantle. Theia was not a stray asteroid. It was not a comet. It was a planet that had formed in a gravitational sweet spot in Earth's orbital neighbourhood, a region called a Lagrange point, where the competing gravitational pulls of the young Sun and the young Earth created a temporary stable zone. Over millions of years, small gravitational perturbations disturbed that stability. Theia drifted. Its orbit shifted, and at some point between 4.4 and 4.5 billion years ago, it found itself on an intersecting path with the body that would eventually become Earth. The collision that followed was not a simple impact. It was a merger, a grinding, catastrophic collision that lasted hours and permanently altered the structure of both worlds. The impact was oblique, a glancing blow rather than a direct strike, and that angle made all the difference. A direct collision at that mass and velocity would likely have destroyed both bodies or merged them into a single dense molten sphere. Instead, the oblique impact transferred enormous angular momentum into the system. It injected Theia's iron core deep into the Earth, merging with the Earth's own core and explaining why our planet's iron core is proportionally larger than planetary formation models would otherwise predict. Meanwhile, the lighter silicate material from both Theia's mantle and Earth's outer layers was ejected into orbit as an enormous disk of vaporized rock debris and molten droplets. This disk of ejecta circled the young Earth in a band extending from inside what is now the International Space Station's orbit out to perhaps 2 or 3 times Earth's current radius. Within tens of millions of years, gravitational accretion gathered this material into the object we call the Moon. The Moon that formed from this debris was not the Moon you know, it was terrifyingly close. Early orbital models suggest the Moon may have initially coalesced at a distance of perhaps 22 to 25,000 kilometers from Earth's center. To put that in perspective, the Moon is currently 384,000 kilometers away. The Moon formed at roughly 1/16 of its current distance. In the sky of the early Earth, the Moon would have appeared approximately 14 to 20 times larger in angular diameter than it does today. The tidal forces it exerted would have been staggering by comparison to anything we experience now. The solid rock of the early Earth, to the extent it had solidified at all, would have been deformed by tidal bulges tens of meters high. Proto-oceans, if any liquid water existed at all, would have experienced tides hundreds of meters tall. The Moon's gravitational grip on this young planet was absolute. The Earth was also spinning much faster in those early days. The impact from Theia imparted enormous angular momentum to the merged system, and the resulting planet completed a full rotation in somewhere between 5 and 6 hours. A day on the early Earth was 5 or 6 hours long. The sun rose, crossed the sky, and set in less time than most modern humans spend at work. This rapid spin had profound implications for the relationship between Earth and Moon. A faster spinning Earth generates stronger tidal forces, and crucially transfers angular momentum to the Moon more rapidly than a slow spinning Earth would. The mechanism responsible for this transfer is elegantly simple and deeply consequential. It involves a bulge of Earth's material perpetually chasing the Moon across the sky, perpetually failing to keep up, and in that perpetual failure, continuously pumping energy and angular momentum from Earth's rotation into the Moon's orbit. This is the engine of lunar recession. It has never stopped. The man who first worked out the mathematics of this process in rigorous detail was George Howard Darwin, son of the naturalist Charles Darwin. In 1879, George Darwin published a series of papers on the tidal evolution of the Earth-Moon system that were remarkable for their era and remain foundational to the field today. Darwin was working with limited data and computational tools that pale beside what we have now, but his physical intuition was extraordinary. He understood that the Moon raises a tidal bulge on Earth, that the Earth rotates faster than the Moon orbits, and that this carries the tidal bulge slightly ahead of the Moon's position in orbit. This offset bulge exerts a gravitational pull on the Moon that has a small component in the direction of the Moon's orbital motion, and a force in the direction of an orbit does not speed an object up in the way you might expect. It lifts it into a higher orbit. This is Newtonian orbital mechanics, operating without pause, without exception for 4.5 billion years. The mechanism works like this. As Earth rotates, its tidal bulge, the physical deformation of Earth's solid rock, ocean and atmosphere caused by the Moon's gravity, is dragged slightly ahead of the Earth-Moon line. This happens because Earth rotates faster than the Moon orbits. The bulge wants to align perfectly with the Moon, but Earth's rotation carries it slightly forward. The Moon, looking back at this ahead-running bulge, sees a concentration of mass slightly in front of the Earth-Moon line. That mass pulls the Moon forward in its orbit. Being pulled forward in an orbit, counterintuitively, causes an object to move into a higher orbit. This is because the increased energy raises the orbital altitude. Meanwhile, the friction of the tidal bulge dragging against Earth's interior acts as a brake on Earth's rotation. Earth slows down. Energy and angular momentum locked in Earth's rotation are continuously and irreversibly transferred into the Moon's orbit. The Moon moves outward. Earth's day grows longer. Both processes are happening right now. Before 1969, the rate of lunar recession was theoretical. Astronomers and physicists understood the mechanism and could estimate the rate from tidal friction models and from the geological record, but they had no direct measurement of sufficient precision. That changed on July 21, 1969, when astronauts Neil Armstrong and Buzz Aldrin placed a small device on the lunar surface before leaving for the last time. That device was a retroreflector array, a panel of corner cube prisms designed to reflect a laser beam directly back toward its source, regardless of the beam's exact angle of incidence. The purpose was to allow observatories on Earth to bounce a laser pulse off the Moon and time the return journey with sufficient precision to calculate the exact Earth-Moon distance. Armstrong and Aldrin's reflector was followed by additional arrays placed during Apollo 14 and Apollo 15 in 1971. These three arrays, still functional today, represent humanity's most precise rulers for measuring the Earth-Moon distance. Modern lunar laser ranging is conducted from several observatories around the world, including the Apache Point Observatory Lunar Laser Ranging Operation in New Mexico, known as Apollo, which achieved first light in 2006. The technique involves firing a powerful pulsed laser toward one of the retroreflectors on the Moon, waiting approximately 2.5 seconds for the light to make the round trip and detecting the returning photons, typically just a handful out of the quintillions sent. From the precise time of flight measurement, astronomers can calculate the Earth-Moon distance to an accuracy of better than 1 millimeter. This extraordinary precision has allowed scientists to measure not just the recession rate of 3.8 centimeters per year, but also subtle variations in that rate caused by the non-uniform distribution of mass within the Moon, the gravitational effects of the Sun, and the fluid dynamics of Earth's oceans. The Moon's distance is now the best measured large astronomical distance in the entire history of science. The Earth-Moon system is a closed angular momentum budget Angular momentum, that quantity that measures how much a system is spinning, cannot be created or destroyed within an isolated system. It can only be transferred between components. Right now, Earth's rotation carries the dominant share of the system's angular momentum. The Moon holds the rest in its orbital motion. The tidal mechanism is steadily transferring this quantity from Earth's rotation to the Moon's orbit, slowing the Earth and expanding the Moon's orbit in the process. This transfer is not metaphorical. It is measurable. It is as real and as constant as gravity. Every single day, a small but precise fraction of Earth's rotational energy makes its way into the Moon's orbit. The total amount of this quantity in the system does not change. What changes is where it lives. And over billions of years, the consequences of where this quantity lives are vast, irreversible, and deeply tied to the conditions that made complex life possible. The tides you experience at the ocean's edge are the most visible manifestation of a process that extends through every layer of Earth. The solid crust of Earth bulges by as much as 30 centimeters in response to the Moon's gravity, a fact that most people have never heard and would find difficult to believe. The oceans, being liquid, respond more dramatically, with tidal ranges at certain coastlines reaching 15 meters or more, as in the Bay of Fundy in Canada. Even the atmosphere has a tidal response to the Moon, a phenomenon so subtle it requires precise barometric sensors to detect. All of these tidal responses are expressions of the same gravitational gradient, the fact that the Moon pulls harder on the near side of Earth than on the far side. This differential force deforms Earth, drags the deformation forward as Earth rotates, and in the dragging continuously bleeds rotational energy from the planet in the form of heat and orbital energy transferred upward into the Moon's ever-widening path. How much is Earth's rotation actually slowing? The measurement is precise. Every year, a day on Earth becomes approximately 1.8 milliseconds longer. That sounds like nothing. In your lifetime, you will never notice it. In 10,000 years, the accumulated difference amounts to roughly 18 seconds. In a million years, the day will be approximately 30 minutes longer than it is today. This is geological change, not a human-scale change, and that is exactly why we tend to dismiss it as trivial. But the geological record does not dismiss it. Corals grow in a way that records the length of the day, depositing a thin ring each day and a broader seasonal band each year. By counting the daily rings between seasonal markers, geologists can calculate how many days were in a year when the coral was alive. More days in a year means shorter days, and the ancient corals are unambiguous. They record a world where days were shorter, years had more of them, and the Moon was closer. The data from ancient corals and stromatolites, those layered bacterial mats that are among the oldest life forms on Earth, paint a consistent picture. In the Devonian period, approximately 400 million years ago, a year contained roughly 400 days, meaning each day was only about 22 hours long. In the Cambrian period, 500 million years ago, a year may have contained over 400 days. Going further back 2 billion years ago, the day may have been only 18 hours long. At the time of the Moon's formation 4.5 billion years ago, the day was between 5 and 6 hours long. This progression from a 5-hour day to a 24-hour day, stretched across 4.5 billion years, is a direct record of the tidal friction that has been breaking Earth's rotation since the moment the Moon entered orbit. Every coral, every stromatolite, every ancient tidal flat preserved in sedimentary rock is a page in the same slow story of departure. As Earth's rotation slows and the Moon's orbit expands, the Moon's orbital period, the length of a lunar month, changes too. The Moon currently completes an orbit of Earth in approximately 29.5 days. But in the deep past, when the Moon was closer, it orbited faster. 4 billion years ago, a lunar month may have been as short as 9 or 10 days. The ancient sky would have been unrecognizable. The moon would have moved noticeably from night to night, rising full and then, only days later, slipping into crescent and then new moon and then crescent again. The cycle we now track over nearly a month would have completed in just over a week. Tides would have pounded the shore at frequencies and amplitudes that no modern coastal ecosystem would recognize as familiar. The connection between the moon's position in the sky and the state of the sea below was intimate and urgent in ways it can never be today. And the legacy of that intimacy is written into the deepest layers of Earth's biological history. Let us turn from the past to the future, from what was to what will be. The same equations that tell us where the moon was 4 billion years ago tell us where it is going. And the picture those equations paint is one of slow, inevitable, permanent change. The moon is not going to drift away to infinity at the current rate. It is not going to escape the Earth-Moon gravitational bond within the Earth's remaining lifetime. At 3.8 centimeters per year, the moon would need approximately 10 billion years to travel another 384,000 kilometers from its current position, effectively doubling its orbital distance. The Earth will not exist in its current form for 10 billion years. The Sun itself has only approximately 5 billion years of hydrogen-burning life remaining. So the contest is not between the moon and Earth. It is between the moon's recession and the sun's death, and the sun will win. But between now and then, the changes the moon's recession drives are not trivial, they are fundamental. There is a boundary in orbital mechanics called the Roche limit, named for French astronomer Édouard Roche, who described it mathematically in 1848. The Roche limit is the minimum orbital distance at which a moon can survive the tidal forces of its parent planet. Below that distance, tidal forces tear the moon apart faster than self-gravity can hold it together. For the Earth-Moon system, the Roche limit sits at approximately 9,500 kilometers from Earth's center. The moon has been safely outside this limit since its formation from the debris disk. But the debris disk itself formed inside the Roche limit, which is why the material first gathered into a ring and then accreted outward before forming a stable moon. The moon began its life just outside the zone where it would have been destroyed. It has been moving away from that boundary every year since. The recession is not a process moving toward destruction. It is a process that began at destruction's edge and has been moving steadily, patiently outward toward a new kind of consequence distance. 3.8 centimeters per year is the current recession rate. But it has not been 3.8 centimeters per year throughout Earth's history, and this is one of the places where the story becomes genuinely complicated. The recession rate is not constant. It depends on how efficiently Earth converts the moon's tidal energy into heat, and that efficiency depends on the state of Earth's oceans and continents. When the continents are arranged so that ocean basins resonate with tidal frequencies, tidal friction is enhanced and the recession rate increases. When the continents are configured differently, tidal energy dissipation is less efficient and the recession rate slows. This has been confirmed by models showing that if the current recession rate of 3.8 centimeters per year had held constant for the entire 4.5 billion year history of the Earth-Moon system, the moon would have been inside the Roche limit as recently as 1.5 billion years ago. It was not. The rate has varied considerably throughout geological history, shaped by the shifting dance of the continents. The geological record of ancient tidal patterns gives us a way to check the orbital models against real data. Tidal rhythmites, layered sedimentary deposits that form in tidal environments and preserve the rhythm of the tides in their lamination, have been found at sites dating back to more than 3 billion years ago. The patterns in these rocks, the thickness of each daily tidal layer, the spacing of springtide and neap tide cycles, encode the orbital parameters of the moon at the time they were deposited. Scientists, including Charles Sonnet at the University of Arizona, analysed tidal rhythmites from the Precambrian period and found that the data was consistent with the Moon moving away more slowly during some intervals and faster during others, driven by the changes in continental configuration and ocean basin geometry. The current 3.8 centimeters per year reflects the particular resonance characteristics of today's ocean basins. It is a snapshot, not the average. It is the rate specific to this configuration, this arrangement of land and sea, this moment in the planet's tectonic story. What we can say with confidence is this: the Moon is currently at 384,400 kilometers from Earth and moving away at 3.8 centimeters per year. The direction is unambiguous. The rate is well established by more than 50 years of lunar laser ranging data. And the physical consequences of that trajectory played out over the timescales relevant to complex life on Earth are among the most underappreciated facts in planetary science. Most discussions of the Moon's recession stop at the measurement. They confirm the rate, note that it seems harmless, and move on. But the measurement is not the story. The story is what the Moon is doing for Earth right now, and what gradually happens to Earth as the Moon's grip on this planet loosens. To understand that story fully, you need to understand three things: the Moon's role in stabilizing Earth's axial tilt, the role tides have played in shaping life, and the extraordinary cosmic coincidence of the total solar eclipse, which is quietly, measurably running out. The first and most consequential thing the Moon does for Earth is hold its axis still. Earth's rotational axis is currently tilted at approximately 23.5 degrees relative to the plane of its orbit around the Sun. This tilt is responsible for the seasons. Without it, there would be no summer or winter. The Sun would track the same arc across the sky every day of the year. The polar regions would be in permanent twilight. The tropics would be in permanent glare. The climate zones as we know them, with their rich latitudinal gradients of temperature and precipitation, would not exist. The extraordinary biodiversity that has developed in response to seasonal variation, the migrations, the flowering cycles, the vast ranges of temperature-adapted species would be absent. 23.5 degrees is not an arbitrary number. It is one of the key parameters that defines the entire climate system of this planet, and it is stable, or more precisely, it is stabilized. Something is holding it in place. That something is the Moon. Earth's axial tilt is not perfectly fixed. It varies between approximately 22 and 25 degrees over a cycle of approximately 41,000 years, a variation known as the obliquity cycle. This variation is one component of the Milankovitch cycles, a set of overlapping astronomical rhythms that modulate Earth's ice ages and warm periods. But the variation is small, only a few degrees, and it's constrained. It is prevented from ranging wildly by the gravitational influence of the Moon. The Moon's gravitational field stabilizes Earth's precessing axis in a way that prevents large amplitude oscillations. This stabilization works because the Moon's mass and proximity create a gravitational torque on Earth's equatorial bulge that resists the perturbations from Jupiter and Saturn, which are the main forces attempting to tip Earth's axis. Without the Moon's stabilizing torque, those perturbations from the giant planets would drive Earth's axial tilt through wild, chaotic oscillations. The obliquity would not vary between 22 and 25 degrees. It would vary between near zero and nearly 85 degrees, and the implications of that are devastating. In 1993, astronomer Jacques Lascar at the Bureau des Longitudes in Paris published a paper in the journal Nature that sent a quiet shock through the planetary science community. Lascar and his collaborator Philippe Roboutel had run numerical simulations of Earth's axial evolution with the Moon removed from the system. The results were stark. Without the Moon, Earth's axial tilt does not vary in the gentle, well-behaved Milankovitch cycles we know. Instead, it evolves chaotically. The obliquity can drift through very large angles over tens of millions of years. In Laskar's simulations, a moonless Earth could have its axial tilt wander from near zero, which would eliminate the seasons entirely, to angles approaching 85 degrees, which would tip the poles toward the Sun for half the year and create temperature extremes that would render most of today's habitable regions unrecognizable. The range of possible obliquity values for a moonless Earth is not a gradual drift. It is a chaotic walk through a vast parameter space with no preferred resting point and no mechanism to bring it back. The best evidence we have for what Earth would look like without the Moon is not a simulation. It is the planet Mars. Mars has two moons, Phobos and Deimos, but they are tiny captured asteroids, nothing like our moon. Phobos is about 27 kilometers in diameter. Their combined mass is negligible. They provide essentially no stabilizing torque on Mars's rotational axis, and Mars's axial tilt, according to long-term orbital calculations, has indeed behaved chaotically over the past few billion years. Current estimates suggest Mars's obliquity has ranged from as little as 10 degrees to as much as 60 degrees over the last few 100 million years alone, with some models allowing excursions approaching 80 degrees over longer timescales. There is abundant geological evidence on Mars for dramatic past climate changes consistent with large obliquity swings, ancient glacial deposits at low latitudes, polar ice that varies dramatically in volume, and geochemical signatures suggesting a climate history that bears almost no resemblance to its present frozen, thin-aired surface. Mars without a large moon is the experiment. Earth with one is the result. If Earth's axial tilt drifted to near zero, the seasons would vanish, the poles would remain cold, the equator warm, but the sharp annual temperature cycle that drives so much of Earth's biology would disappear. Ecosystems that depend on seasonal triggers, from flowering plants to migratory birds to the breeding cycles of countless species, would face conditions evolutionary biology has not prepared them for. If the tilt went to the other extreme, approaching 80 or 85 degrees, the result would be catastrophic in different ways. At high obliquity, the polar regions tilt nearly directly toward the Sun during the respective hemispheres' summer. Temperatures at the poles would reach values currently seen in the tropics. Meanwhile, the tropics would experience cooler average temperatures, spending more time at high angles to the Sun. The climate belts would invert and then oscillate as the tilt changed. Ice would form and melt in patterns that no ecosystem could track. Complex life requires stability across geological time. Chaotic obliquity is the most efficient mechanism the solar system has for denying that stability. How long will the Moon continue to stabilize Earth's axial tilt? This is a question with no perfectly clean answer, because the Moon's stabilizing influence is not a switch that turns off at a specific distance. It fades gradually as the Moon recedes and its gravitational torque on Earth's equatorial bulge weakens. Laskar's subsequent work has suggested that even with the Moon present, Earth's obliquity may begin to show signs of increased variability over very long timescales as the Moon moves further away. But for the next several 100 million years, the Moon's stabilizing effect remains dominant. The question becomes more pressing at timescales beyond 1 billion years, when the Moon will have receded by an additional 3,800 kilometers. The margin of stability is not infinite, and the margin is eroding, not quickly, not dramatically, but the physics is moving in one direction and has been for 4.5 billion years. The tilt that gave us seasons, agriculture, biodiversity, and civilization is on borrowed time. borrowed from a moon that has been slowly asking for it back since the beginning. The second great contribution the moon makes to Earth's habitability is its tidal engine. The tides have been one of the primary drivers of biological evolution on this planet, and the implications extend far beyond the rhythm of high water and low water at the beach. The intertidal zone, that strip of coastline alternately submerged and exposed twice daily, is one of the most biologically productive and evolutionarily significant environments in the history of life on Earth. The creatures that learn to survive the intertidal transition, to handle air exposure during low tide and re-immersion during high tide, were undergoing a training regime for one of the most consequential evolutionary experiments in history: the conquest of land. The first fish to haul themselves out of the water and survive for minutes in the air were adapting to the demands of the intertidal zone. The lungs you are using right now to breathe are, in a very real sense, a tidal adaptation, a gift from the moon to the land creatures who would eventually inherit the planet. There is a deeper connection between tides and the origin of life itself. Before complex organisms, before cells with membranes, before DNA as we know it, there was the question of how biological molecules could concentrate enough to begin self-replication. The primordial ocean was thin. Concentrations of the molecules needed for chemistry to become biology were too dilute for reactions to happen reliably. But the intertidal zone provides a concentrating mechanism. At low tide, pools of seawater are isolated from the ocean. The sun evaporates the water. The molecules dissolved in it concentrate. At high tide, the pool refills with new material. The cycle repeats over and over across millions of years. This tidal concentration mechanism was first proposed by Charles Darwin himself in an 1871 letter and has been developed extensively by origin of life researchers in the decades since, including Jack Szostak, who shared the Nobel Prize in Physiology or Medicine in 2009 for his work on RNA self-replication in environments that include tidal concentration effects. The moon did not just enable life to reach land, it may have helped start life in the first place. The tides also interact with continental geology in ways that matter for the long-term habitability of Earth. Tidal currents sweep nutrients from the deep ocean floor to the surface, a process called tidal upwelling that supports some of the most productive marine ecosystems on the planet. The Grand Banks off Newfoundland, one of the richest fisheries in history, owes much of its productivity to this mechanism. The coastal shelves of the world, where tidal mixing is most intense, are disproportionately productive compared to the open ocean. Without tidal mixing, the deep ocean's nutrients would remain locked in the cold, dark depths far from the sunlit surface zone where photosynthesis occurs. Lower ocean productivity means less oxygen produced over geological time. Less oxygen means a different atmosphere. A different atmosphere means a different planet. The moon's tides are woven into the chemistry of the air you are breathing right now. Remove the moon, weaken the tides, and the cascade of consequences reaches back through 1 billion years of atmospheric evolution. As the moon recedes, the tides will weaken. The strength of the tidal force scales as the inverse cube of the distance. This is not the same as gravity, which scales as the inverse square. The inverse cube relationship means that tidal force weakens much more rapidly with distance than ordinary gravitational attraction does. If the moon were twice as far away as it is today, that tidal force would be 1/8 as strong. In 1 billion years, when the moon has receded by an additional 3,800 kilometers, roughly 1% of its current distance, the tidal force will be reduced by approximately 3%. That sounds small, but projected over 10 billion years, the moon would be perhaps 10% more distant, and tidal forces would be reduced by roughly 27% from today's values. The oceans would still have tides. They would be smaller, quieter, and less biologically consequential. The intertidal zone would narrow, the mixing would slow, the ocean's biological productivity would decline. The planet that emerges from that process is the diminished version of the one we inhabit now. The third great consequence of the Moon's current position is also the most visually spectacular and most obviously temporary, the total solar eclipse. A total solar eclipse, in which the Moon perfectly covers the disk of the Sun for a few precious minutes, is one of the most extraordinary visual phenomena available to any observer on the surface of a rocky planet. It does not happen because the Moon and Sun are the same size. They are nowhere near the same size. The Sun is approximately 400 times larger in diameter than the Moon. The reason total eclipses are possible is that the Sun is approximately 400 times farther from Earth than the Moon. These two factors cancel each other almost precisely, producing an almost exact match in the apparent angular size of the two objects in Earth's sky. The Sun's disk spans approximately half a degree as seen from Earth. The Moon's disk also spans approximately half a degree. This coincidence is, in the full 4 billion year history of the solar system, a brief and extraordinary window that is currently open and currently closing. The Moon is moving away. As it recedes, its apparent angular size in Earth's sky shrinks. The Sun's apparent size is not changing on any relevant timescale, so the gap between the Moon's apparent size and the Sun's apparent size is growing, slowly but irreversibly. Right now, the Moon's apparent diameter is very slightly larger than the Sun's on average, which is why total eclipses happen at all, and also why we sometimes have annular eclipses when the Moon is near the far end of its elliptical orbit, and its apparent disk is just barely smaller than the Sun's, leaving a ring of sunlight visible around the lunar edge. As the Moon continues to recede, annular eclipses will become the norm. Total eclipses, where the Moon completely blocks the Sun's disk, will become rarer and eventually impossible. The last total solar eclipse visible from Earth is estimated to occur in approximately 600 million to 800 million years. That is a long time, long enough that it feels abstract. But the mechanism delivering that outcome is operating right now. Total solar eclipses have given humanity some of its most important astronomical data. The solar corona, the Sun's outer atmosphere, is visible to the naked eye only during a total eclipse, because at all other times the corona's dim glow is overwhelmed by the Sun's direct light. Scientists have used total eclipses to study the corona's structure, temperature, and dynamics for over a century. Research that continues today in the quest to understand why the corona is millions of degrees hotter than the Sun's surface, a mystery that remains unsolved. Total eclipses also provided the first empirical test of Einstein's general theory of relativity. In 1919, during a total solar eclipse visible from the island of Príncipe off the west coast of Africa, astronomer Arthur Eddington measured the apparent deflection of starlight passing near the Sun, confirming Einstein's prediction that massive objects curve space-time. That confirmation changed physics, and it was only possible because a moon happened to be precisely the right angular size to block the Sun's disk at precisely the right moment in geological history. The probability of any given planet having a moon that so precisely matches the apparent angular size of its star is extremely low. For this coincidence to hold, the moon's size and its orbital distance must be tuned to each other and to the star's size and distance in a way that no known law of planetary formation requires. Most moons in the solar system do not produce total eclipses of their parent star. Jupiter's moons produce annular eclipses. Mars's moons are so small they produce only tiny transits across the Sun's disk. Our moon's angular size is, from a statistical standpoint, a remarkable accident of history, and it is an accident that is expiring. Every year, as the moon moves 3.8 centimeters further from Earth, the window of total eclipses narrows. We happen to be alive in the window. We happen to be living in the epoch of cosmic history, when looking up at the sky and seeing the moon exactly cover the sun is possible. The window is open, but it has a closing time, and physics is holding the door. The slowing of Earth's rotation, driven by the same tidal friction that pushes the moon outward, has consequences beyond the day length itself. As Earth's rotation slows, its equatorial bulge shrinks slightly because the bulge is maintained by centrifugal force. A slower spinning Earth is more nearly spherical. A more spherical Earth has a slightly different gravitational field. The angular momentum distribution within the planet changes subtly. These changes feed back into the atmospheric circulation patterns, the Hadley cells and the jet streams, which depend on the Coriolis force generated by Earth's rotation. A slower spinning Earth would have weaker Coriolis deflection, altering weather systems, changing where storms form and how long they persist. The zones of latitude-dependent climate would shift. Hurricanes, which draw their rotational character from the Coriolis force, would behave differently. None of these changes happen on human timescales. They happen on geological timescales, but they are all part of the same slow process that started when Theia hit the early Earth 4.5 billion years ago, and the tidal engine first switched on. Let us project the moon's recession into the specific future to understand what the milestones look like. In 600 million years, the moon will have receded by an additional 23 kilometers. The total solar eclipse window will have closed. No creature on Earth's surface will ever again see the moon perfectly cover the sun. In 1 billion years, the moon will be approximately 3,800 kilometers further out than today. Tidal forces will be roughly 3% weaker. Day length will have increased by approximately 40 minutes. These are not dramatic changes by geological standards. The moon will still dominate the night sky. Tides will still exist. The axial tilt will still be substantially stable, but the trajectory is fixed, the direction unalterable, and each of these individual changes, tiny as they are in isolation, feeds into larger changes playing out across the 3 to 5 billion year scale, where the sun's own evolution begins to dominate the story and rewrite the ending in a way that the moon's recession alone never could. In 5 billion years, the sun will begin to exhaust its core hydrogen and enter the red giant phase of stellar evolution. Over approximately 1 billion additional years, it will expand enormously, ultimately swallowing Mercury and Venus and potentially reaching close to Earth's orbit. As the sun expands, its gravitational influence on the Earth-Moon system will grow. The sun's tidal force on Earth will increase as the sun's radius increases. At the same time, the sun's increasing luminosity will cause Earth's oceans to evaporate, eliminating the ocean tidal dissipation that is currently the dominant driver of lunar recession. As the oceans vanish, tidal efficiency will drop dramatically. The recession rate may slow considerably, but the sun's expanding mass and radius will increasingly perturb the moon's orbit. The moon's recession becomes entangled with the sun's own expansion. The scenario is not one where the moon drifts peacefully to infinity while Earth is quietly engulfed. It is more complex, more chaotic, and more final than that picture suggests. When the sun becomes a red giant, tidal interactions between the expanded sun and Earth's orbit will also gradually cause Earth to spiral inward. The same tidal mechanism that pushes the moon outward from Earth will cause Earth to spiral slowly toward the expanding sun. This is because Earth is now the smaller, faster orbiting body relative to the enormous, slowly rotating red giant sun, which means the energy transfer runs in the opposite direction. The tidal bulge raised on the expanded sun by Earth will lag behind the Earth-Sun line, and the resulting torque will drain angular momentum from Earth's orbit, causing it to shrink rather than grow. Earth and the moon will not drift into the cold dark forever. They will be drawn into the sun's expanding envelope and consumed. The moon's recession, which began at the moment of formation, will end not in distance but in dissolution, consumed by the same stellar furnace that will ultimately reclaim everything in the inner solar system. The Thear impact will finally be complete, the debt will finally be settled. There is a solar system body that shows us exactly where the Earth-Moon system is heading, a system that has already completed the process still in progress here. The Pluto-Charon system. Pluto and its largest moon Charon are mutually tidally locked. Each body always shows the same face to the other. From Pluto's equatorial regions, Charon hangs in the sky without moving relative to the horizon. The tidal breaking is complete. The angular momentum transfer is finished. Pluto's rotation and Charon's orbit have reached final equilibrium. Earth and Moon are travelling toward this same destination. The Moon is currently locked to Earth, showing us only one face because the Moon reached its tidal lock state long ago, within 1 billion years of its formation. Earth has not yet locked to the Moon because Earth is so much more massive that tidal breaking of its rotation takes far longer. Earth's day is still lengthening. The experiment is underway. It has been underway for 4.5 billion years, and the Sun will end it before it completes. What would Earth have been like if the Moon had never formed? If the R had missed, or if the impact occurred at an angle that prevented a large moon from coalescing? The answer, according to several decades of modelling, is that Earth would have been a significantly less hospitable place for complex life. Without the Moon's stabilising torque, the axial tilt would have wandered chaotically, producing climate extremes incompatible with the long-term stability of complex ecosystems. Without strong tides, the intertidal zone would have been narrower and less dynamic, potentially slowing or preventing the transitions that moved life from sea to land. Without a large moon to slow Earth's rotation, the day would have remained much shorter, driving more intense atmospheric circulation and more violent weather systems. Without the energy deposited by the Thear impact, Earth's core may have been in a different thermal state, affecting the longevity of the magnetic field that protects the surface from the solar wind. The Moon is not just present in Earth's story, it is one of its principal architects. Planetary scientist Peter Ward and astronomer Donald Brownlee explored the Moon's contribution to Earth's habitability in their 2000 book Rare Earth: Why Complex Life is Uncommon in the Universe. Their argument was that the combination of a large stabilizing moon, a location in the habitable zone of a quiet star, and several other conditions might make Earth-like complex life far rarer in the universe than the optimistic assumptions of the early search for extraterrestrial intelligence community had supposed. The Moon appeared prominently in their analysis as a near-essential contributor to the stability of Earth's climate over the timescales needed for complex life to evolve. Their hypothesis remains debated. Some researchers argue that life could adapt to a wider range of obliquity conditions than Rare Earth assumes, but the basic point that a large stabilizing moon represents a significant advantage for any planet trying to maintain long-term climate stability suitable for the emergence of intelligence is broadly accepted in contemporary planetary science as a serious factor in the cosmic accounting of habitable worlds. In the last 3 decades, the discovery of exoplanets has transformed our ability to think about these questions empirically. We now know of more than 5,000 confirmed planets orbiting other stars, with tens of thousands more candidates awaiting confirmation. But we know almost nothing about their moons. Exomoon detection is at the very frontier of observational capability. A small number of exomoon candidates have been tentatively identified, but none confirmed with the same confidence level we apply to exoplanet detections. What we can say is that the conditions required to produce a large stabilizing moon specifically a giant impact event that throws the right amount of material into orbit at the right distance to coalesce into a moon of significant mass, are not trivially reproduced. Giant impacts are common in the early solar system, but vary enormously in their outcomes. Many produce no moon, or produce small moons with negligible stabilizing effect. The moon's formation was a specific kind of event with a specific range of favorable outcomes. Whether it is common or rare in the broader galaxy is one of the most important open questions in astrobiology. The Drake equation, formulated by astronomer Frank Drake at a small conference in Green Bank, West Virginia in 1961, attempts to estimate the number of communicating civilizations in the Milky Way by multiplying together a series of factors, each representing a probability in the chain from star formation to intelligent communication. One of those factors, the fraction of habitable planets that develop complex life, depends critically on how stable the planet's climate is over geological timescales. If the moon's stabilizing role is essential for the emergence of complex life, then the relevant factor in the Drake equation is multiplied by the probability that any given rocky planet in a habitable zone has acquired a large stabilizing moon. If that probability is low, the number of communicating civilizations drops accordingly. The moon's recession is not just a story about Earth's future. It is a data point in the most profound question humanity has ever asked. How common is life? How common is intelligence? And how alone in this enormous universe are we? Let us return to the measurement. 3.8 centimeters per year. This number was not guessed. It was not estimated from indirect evidence alone. It was measured directly, repeatedly, by bouncing lasers off mirrors left on the moon, by human beings who travelled there during a 10-year period when humanity was briefly capable of visiting another world. The retroreflectors placed by Apollo 11, 14 and 15 are the most enduring scientific instruments ever left on another world. They have been in continuous use since their placement. In 2006, the Apollo instrument at Apache Point Observatory in New Mexico achieved a measurement precision better than 1 millimeter over the 384,000 kilometer round trip. This is equivalent to measuring the distance from Los Angeles to New York to an accuracy of 1/400th of the width of a human hair. The moon is moving away from us. We know exactly how fast. We know exactly how it works. The measurement is not in doubt. What most people do not appreciate is the magnitude of what that number implies. The precision of lunar laser ranging has given scientists far more than just the recession rate. The tiny variations in the moon's distance from Earth over time encode information about the moon's internal structure, the distribution of mass within its interior, the behavior of its fluid core, and the degree to which the moon is not perfectly rigid. The moon flexes, very slightly, in response to Earth's gravitational field, and the amount of that flexing tells us something about the physical state of the moon's deep interior. Lunar laser ranging has also been used to test the equivalence principle of general relativity, Einstein's prediction that all objects fall at the same rate regardless of their composition, by comparing the way Earth and Moon fall toward the Sun. Einstein's equivalence principle has passed this test to extraordinary precision. The mirrors on the Moon are not just measuring the Moon's distance, they are simultaneously, with every returning photon, testing the fundamental laws of physics with an accuracy that no ground-based laboratory can match. While telescopes and lasers measure the Moon from above, the geological record measures it from below, encoded in the rhythm of ancient sediments and the growth patterns of long-dead organisms. Perhaps the most remarkable of these geological clocks is the tidalite, a type of sedimentary deposit that forms in tidal environments and preserves the rhythm of the tides in its layering. Tidalites from the Precambrian era, deposited more than 800 million years ago, have been analysed by multiple research groups who found that the tidal patterns preserved in these ancient rocks are consistent with a moon that was closer, orbiting faster, and driving stronger tides than it does today. The data from the rocks and the data from the orbital models agree. They are telling the same story from two very different directions, and the story they are telling is this: the moon has always been leaving. It has been leaving since the moment it arrived. Every tidal flat, every ancient coral, every laminated sediment is a pay in the same slow farewell written in stone. Stromatolites are among the oldest complex structures on Earth. Layered mounds built by communities of photosynthetic bacteria that trap and cement sediment with each day's growth. The oldest known stromatolites date back at least 3.7 billion years, and possibly to 3.48 billion years, making them among the oldest direct evidence of life. What makes stromatolites extraordinary for the story of the moon's recession is that they record not just the presence of life, but its daily and monthly rhythm. The growth laminae in stromatolites can be counted, and the pattern of neap and spring tides preserved in their structure gives planetary scientists a window into the lunar orbit of billions of years ago. John Wells of Cornell University pioneered this approach using coral growth rings in the 1960s, and the method has since been extended and refined using stromatolite records from across the world. These microbial mats are not just beautiful ancient structures, they are diaries written in mineral and carbonate, documenting the moon's precise position in Earth's sky across incomprehensible spans of time. Here is the disconnect that makes this entire story difficult to absorb. Everything described so far, the slowing of Earth's rotation, the recession of the moon, the weakening of tides, the changing climate, the closing of the eclipse window, all of it happens on timescales profoundly alien to human experience. The fastest of these processes, the closing of the total eclipse window, takes 600 million years. The next ice age, by comparison, is perhaps 100,000 years away. The entire history of anatomically modern Homo sapiens spans only about 300,000 years. The agricultural revolution began 12,000 years ago. The industrial revolution began less than 300 years ago. When we say the moon has moved 3.8 centimeters further from Earth since you were born, we mean something that is, within the margin of human concern, essentially nothing. The numbers are real, the consequences are real, but the scale at which those consequences unfold is a scale that requires active effort to hold in the mind and even greater effort to genuinely feel. And yet this disconnect is worth sitting with. Most of the processes that have made Earth hospitable for complex life have operated on exactly this timescale: billions of years, hundreds of millions of years. The evolution of the eye required hundreds of millions of years of incremental selection. The oxygenation of the atmosphere required billions of years of microbial photosynthesis. The formation of coal required 300 million years of unfallen forests accumulating organic carbon. Everything that created the conditions for human existence was a process of almost incomprehensible duration. The moon's role in that process, the axial tilt it has held steady, the tides it has driven, the intertidal zone it has maintained, the eclipses it has provided for the greatest scientific discoveries, all of this is part of the same long story. You are standing at a specific point in that story, not the beginning, not the end, somewhere in the middle of a geological saga that was already ancient before the first animal ever drew breath. The moon is still here, but it has always been leaving. There is a photograph from the Apollo 8 mission, taken on December 24, 1968, as the spacecraft came around from behind the moon on its fourth orbit. It shows Earth, blue and white and impossibly fragile, rising above the grey lunar horizon. The photograph is called Earthrise, taken by astronaut William Anders. In it, the moon's barren surface fills the foreground and Earth hangs in the black void above. What almost no one who looks at this image thinks about is that when this photograph was taken, Earth and Moon were in a configuration that has not existed for most of the solar system's history and will not exist for most of its future. The Moon was at its historically unusual distance from Earth. Earth still had its full complement of oceans, its stable tilt, its robust tidal system. The window in which this photograph and everything it represents is possible has been open for approximately 4.5 billion years. It will not stay open indefinitely. Every great photograph has a context. That image's context is a closing window. The Apollo program, which placed 12 human beings on the Moon between 1969 and 1972, returned approximately 382 kilograms of lunar rock and soil samples to Earth. These samples have been analysed in hundreds of laboratories around the world over the past 5 decades and have told us an enormous amount about the Moon's composition, formation, and history. They have confirmed the giant impact hypothesis for the Moon's formation, established the timeline of the late heavy bombardment when the inner solar system was saturated with impacting asteroids and craters were carved across every solid world. But the most enduring legacy of the Apollo missions for the story of lunar recession may be the retroreflectors, those modest panels of corner cube prisms sitting slightly on the lunar surface, bouncing laser pulses back toward Earth year after year, measuring with millimeter precision the number that tells us the Moon is leaving. 3.8 centimeters per year. Apollo ended in 1972. The measurement it enabled is still going, still confirming, still accumulating data. Step outside tonight. If the sky is clear and look at the Moon, depending on where you are in the lunar cycle, you might see a full moon hanging in the southeast or a crescent low in the western sky after sunset, or a gibbous moon rising late in the night. Whatever phase you see, what you're looking at is a world 3,474 kilometers in diameter, hanging in space approximately 384,000 kilometers above your head, moving away from you at 3.8 centimeters per year. Its surface is covered in impact craters, ancient lava plains called the lunar Maria, mountain ranges, and dust so fine the Apollo astronauts said it smelled like spent gunpowder when they tracked it into the cabin. There is no wind on the Moon, no weather, no erosion except the slow gardening of micrometeorite impacts and the unceasing bombardment of the solar wind stripping atomic layers from its surface over billions of quiet years. The face you see is always the same face. The Moon keeps one side permanently toward the Earth because Earth's tidal gravity long ago broke the Moon's rotation until it was synchronized with its orbital period. The Moon rotates once on its axis in exactly the same time it takes to orbit Earth, which is why the far side is permanently hidden from direct view. This state is called tidal locking or synchronous rotation, and it is the final equilibrium of tidal friction. The Moon reached this state within approximately 1 billion years of its formation, because the Moon is so much less massive than Earth that tidal braking of its rotation was relatively rapid. Earth, being far more massive, has not yet been braked to synchronous rotation by the Moon's much weaker tidal grip. Earth's day is still lengthening. The Moon finished its journey to tidal lock billions of years ago. Earth has not. And from the Moon's perspective, Earth is a beautiful blue planet that slowly, endlessly turns before the unblinking face of the locked lunar surface. The far side of the Moon, first photographed in 1959 by the Soviet Luna 3 spacecraft, is dramatically different from the near side, where the near side is dominated by the dark volcanic maria that make up the familiar face of the Moon. The far side is almost entirely covered in the ancient, heavily cratered highlands terrain. The asymmetry has puzzled planetary scientists for decades. One leading hypothesis is that the near side was kept slightly warmer by Earth's early thermal radiation, allowing volcanic activity to resurface it more extensively. Another is that the moon's crust is thinner on the near side for reasons related to the tidal deformation it experienced when it was much closer to Earth. Whatever the cause, the moon that faces us is a different world from the moon that never sees us. The Chinese Chang'e 4 mission landed on the far side in January 2019, the first soft landing on the lunar far side in history, touching down in the South Pole 8Ken Basin, one of the largest and oldest impact craters in the solar system. There is something philosophically significant about the fact that the moon always shows us the same face. It is a reminder that the Earth-Moon relationship, for all its dynamism over geological time, is a relationship of deep intimacy. The moon is locked to Earth. It cannot look away. And from Earth, the moon presents the same features, the same Maria, the same craters, the same ancient volcanic plains night after night, year after year, millennium after millennium. Humans have been looking at this face for our entire existence as a species. It was the same face our ancestors saw by firelight in the Paleolithic, the same face that guided the agricultural calendar of the first civilizations, the same face that navigators used to determine longitude before modern chronometers, the same face that poets and scientists and lovers have stared at for 100,000 years of human history. It is 3.8 centimeters farther away than it was last year, and it is 3.8 centimeters closer than it will be next year. That asymmetry is permanent. Imagine two time travelers, one transported back to Earth 4 billion years ago, one transported forward to Earth 1 billion years in the future, both standing on a beach at night. The time traveller in the past would see a moon so enormous in the sky that it would cover an angular area more than 10 times larger than our moon does today. The tides rolling in would reach heights measured in tens of meters. The day would be 12 hours long or less. The night sky would have a moon so dominant, so overwhelming, so blazingly present, that it would cast sharp shadows far brighter than our full moon does today. The time traveller in the future would see a moon slightly smaller than ours, its tides slightly weaker, its eclipses reduced to annular rings of light rather than total coverage. The night sky would still be recognizable. The moon would still dominate. But the brief and extraordinary epoch in which the moon and sun occupy exactly the same apparent angular size, in which total solar eclipses are possible, would be over. The window would have closed. Human civilization has been so thoroughly shaped by the moon that it is nearly impossible to disentangle our cultural, scientific and practical history from the lunar cycle. The calendar, one of humanity's first and most necessary intellectual achievements, begins with the moon. The Sumerian calendar, one of the earliest recorded, was lunisolar, tracking both the moon's monthly cycle and the sun's annual cycle to schedule planting, harvesting and religious observance. The Islamic calendar remains a purely lunar calendar to this day, with its months defined by the first sighting of the crescent moon after new moon. The Jewish calendar is lunisolar. The dates of Easter, Passover and many other religious observances across multiple traditions are still calculated based on the phase of the moon. The tidal rhythms the moon imposes on the world's oceans have governed fishing, navigation, and coastal construction for 10,000 years of human civilization. Remove the moon and you do not just change the night sky. You remove the organizing principle around which much of human culture was first assembled. Let us return to the number and sit with it one more time, 3.8 centimeters per year. In your lifetime, assuming you live to roughly 80 years old, the moon will move approximately 3 meters farther from Earth. 3 meters, and in the span of a human life, the moon retreats the length of a small room. That is all. And yet this is the same process that has moved the Moon from roughly 22,000 kilometers away at the moment of its formation to 384,000 kilometers today. 3.8 centimeters per year, compounding across 4.5 billion years, produced a change of 362,000 kilometers. The number is not dramatic in a human lifetime, it is devastating across geological time. It is the same mathematical relationship that makes a bank account earning modest interest look unimpressive for the first 20 years and then frighteningly large for the next 40. The Moon's recession is compound interest applied to the solar system. The invoice has been accumulating for 4.5 billion years. The law of conservation of angular momentum is one of the most fundamental laws in physics. It is not a guideline. It is not an approximation. It is a statement about the deep symmetry of space and time derived from Noether's theorem, which shows that conservation laws emerge directly from the symmetries of the laws of physics themselves. Angular momentum is conserved because the laws of physics are symmetric under rotation. This symmetry produces a conserved quantity, and that quantity is angular momentum. In the Earth-Moon system, angular momentum is not being created or destroyed. It is being relocated. Earth's rotation is slowing. The Moon's orbit is expanding. The combined total in the system, combining Earth's spin and the Moon's orbital motion, remains constant. The tidal friction is not violating any physical law. It is precisely impeccably obeying the most fundamental law of mechanics. The Moon is moving away because it has to. It is moving away because physics requires it. No intention, no tragedy, just the universe sorting its accounts. No one decided this would happen. No event in the history of the solar system specifically set the Moon on a course to move away from Earth. It is simply what physics does when a small body orbits a larger, faster spinning body under the influence of tidal friction. The process is universal. It operates in every tidal system in the universe where these conditions are met. It operated in the Pluto-Charon system, bringing both bodies to mutual tidal lock. It operates in the systems of the outer planets, where small inner moons are affected by similar tidal dynamics. It will operate wherever a moon forms close enough to a planet for tidal forces to be significant. The Moon is leaving because the universe has no mechanism for stopping it, given the current configuration of masses, rotation rates and distances. To stop the Moon from moving would require injecting angular momentum into Earth's rotation, or removing it from the Moon's orbit, a task beyond any natural process, and currently beyond any human technology. It is happening, it cannot be undone, and it began before the first cell ever divided. The Moon's gravitational influence extends beyond the solid Earth and the liquid ocean. It also acts on Earth's atmosphere. The atmospheric tide driven by the Moon is small compared to the oceanic and solid Earth tides, detectable only by sensitive instruments. But it is real. More significantly, the Moon may have played a role in the formation of Earth's early atmosphere by helping to drive the volcanic outgassing that built up the original atmospheric gases. The argument runs as follows. The strong tidal forces of the early Moon caused more internal heating of the early Earth, driving more volcanic activity, releasing more water vapor, carbon dioxide and nitrogen into the atmosphere more rapidly than would have occurred without the Moon's intense early tidal pull. If this is correct, the Moon did not just stabilize the atmosphere by locking the axial tilt. It may have helped create the atmosphere in the first place. The connection between the Moon and the air you breathe goes deeper than any single mechanism suggests. It is systemic, ancient, and woven through every layer of Earth's history. There is one more connection between the Moon and Earth's habitability that is less well established, but actively researched. Earth's magnetic field, the magnetosphere, protects the surface from the lethal particle radiation of the solar wind. It is generated by the convective circulation of liquid iron in Earth's outer core. driven partly by the cooling of the core releasing heat and partly by compositional changes in the outer core. Some researchers have proposed that the initial thermal state of Earth's core, and therefore the long-term vigour of the core's convection, was significantly influenced by the energy deposited by the Theia impact. The impact that formed the Moon may have profoundly affected the thermal history of Earth's core, and therefore the strength and longevity of the magnetosphere. Without a strong magnetosphere, the solar wind would have stripped Earth's atmosphere over geological time, as it appears to have stripped Mars's early atmosphere. The Moon's formation may have been a precondition for Earth keeping its air, its water, and therefore everything that followed. Venus provides a useful contrast. Venus is roughly the same size and mass as Earth, formed in the same region of the early solar system, and has no significant moon. Its axial tilt is nearly zero, though while its rotation is retrograde and extremely slow, completing a rotation every 243 Earth days. Its surface is an inferno of 465 degrees Celsius. Its atmosphere 90 times denser than Earth's, and composed almost entirely of carbon dioxide. There is no evidence of liquid water on its surface and no evidence of life. Whether a large stabilizing moon would have made Venus more Earth-like is impossible to say with confidence. The conditions on early Venus may have been so different from early Earth that the comparison is limited, but the contrast is impossible to ignore. Earth has a moon and harbours the only known complex life in the universe. Venus does not have a moon and is a world that no known biology could survive. One data point. One very suggestive data point. None of this was designed. There is no plan in the architecture of the solar system, no purpose in the trajectory of Theia, no intention in the tidal friction that has been breaking Earth's rotation for 4.5 billion years. The processes are as indifferent as gravity itself, which is to say they are completely indifferent. The Moon formed because physical conditions made its formation likely given the Theia impact. The Moon has been receding because tidal friction makes it inevitable given the initial configuration of masses and rotation rates. The Moon will continue to recede until some other process intervenes. Throughout all of this, the universe has had no opinion on the outcome. It did not care whether Earth developed complex life. It did not care whether the Moon would prove crucial to that development. It only cared, if that word can be applied at all, about the conservation of energy and angular momentum. And those laws produced without intent or awareness, without preference or goal, everything that exists on this planet and everything that looks up at the sky and wonders. The Moon is the only world beyond Earth that humans have ever visited. 12 men walked on its surface between 1969 and 1972. The last human footstep on the Moon was made by astronaut Gene Cernan on December 14, 1972, as he climbed back into the Lunar Module Challenger before returning to orbit. Since Cernan's departure, no human has returned to the Moon. NASA's Artemis program represents the first serious attempt to change that in more than 50 years. The Moon that waiting missions will find is the same Moon, slightly farther away. 3.8 centimeters per year for 50 plus years amounts to roughly 2 meters more distant than when the last Apollo crew departed. 2 meters, the entire change across half a century of human spaceflight history. A sustained human presence on the Moon, whenever it occurs, would be something different from Apollo, the beginning of a long-term relationship between humanity and its closest neighbour. On the timescales of human civilization, the Moon's recession is imperceptible. A lunar base built today would not need to be abandoned because of lunar recession for longer than any civilization in history has ever survived. The Moon has been the source of more poetry, mythology, music and art than perhaps any other object in the sky. From cave paintings of the Paleolithic, which some researchers believe incorporate lunar cycle records, to the ancient Mesopotamian moon god Sin, to the Tang dynasty poet Li, by writing of the moon as a companion in exile, to Beethoven's Moonlight Sonata, to the hundreds of contemporary poets for whom the moon remains an inexhaustible subject, humanity has always known that something important is up there. This cultural fixation is not accidental. The moon is the most changeable and most regular object in the sky, cycling through its phases on a schedule precise enough to use as a calendar and variable enough to inspire wonder. It is close enough to show a face, distant enough to remain mysterious. It controls the tides and the rhythm of the sea. It illuminates the night without burning. It is, in the natural world, the closest thing to a companion that is always there and always changing, and its steady departure is the kind of thing that, once you know it, you cannot unknow. What does it mean that the moon is leaving? Not in the practical sense of tidal weakening and eclipse windows and axial tilt, but in the deeper sense of what it means that the most constant presence in the human sky is, in fact, constantly departing. Every phase of the moon ever observed in the history of Homo sapiens was observed from slightly closer than the phase before. Every full moon in human history was a full moon seen from 3.8 centimeters less distance than the next one. The moon that our grandchildren will look at will be slightly farther away than the moon our grandparents saw. The change is immeasurable in a human life. It is undetectable to human senses, but it is real, and there is something in that reality that speaks to the nature of all things. Nothing in the universe is truly static. Everything is in motion. Everything is transitioning. Even the most fixed-seeming presence in our sky is, if you look carefully enough, waving goodbye. Slowly, one tidal cycle at a time, 3.8 centimeters per evolution around the sun. The moon's recession is not a new thing beginning now. It is the continuation of the event that created the moon. The VR impact injected angular momentum into the early Earth-Moon system. Tidal friction has been slowly distributing that angular momentum ever since, transferring it from Earth's rotation to the moon's orbital motion. The recession is not a problem that arose after the moon formed. It is the process by which the moon-forming event is completing itself. The R struck Earth and created a system with a specific total angular momentum. That angular momentum is conserved. It is being sorted, organized, and redistributed. Earth's spin is slowing to accommodate the moon's expanding orbit. The moon is moving outward to carry the angular momentum that Earth can no longer hold. This is not decay. It is not entropy in the common sense. It is a system finding its long-term equilibrium state, a process that will take billions of years and will be interrupted only by the sun's eventual departure from the main sequence. The THR impact is still in progress. We are living inside its aftermath. There is something almost meditative about the patience of physics. The tidal forces that have been breaking Earth's rotation for 4.5 billion years are not dramatic in any given moment. The force of the tidal bulge acting on the moon, transferring angular momentum to it, is weak. The recession it produces is 3.8 centimeters per year. The lengthening of the day it produces is 1.8 milliseconds per year. These are measurements that require extremely sensitive instruments to detect. They are invisible to human senses, they are irrelevant to human daily life, and yet they are writing the future of this planet with the same certainty that gravity writes the trajectory of a falling stone. The tidal engine does not hurry, it does not have deadlines. It simply operates every second of every day, every high tide and every low tide, every drag of the tidal bulge through the imperfect rock and water of Earth's body, steadily, precisely, without pause or interruption, transferring its few millimeters of orbital energy per year into the moon's expanding path around this planet. Take a moment to appreciate the scale of what the moon has accomplished from its position in space. Over 4.5 billion years, it has slowed Earth's rotation from a 5-hour day to a 24-hour day, a change of approximately 19 hours. It has held Earth's axial tilt stable within a few degrees, preventing the chaotic oscillations that have plagued Mars. It has driven the tidal cycles that may have concentrated the biological molecules that became the first life, powered the intertidal evolution that moved life onto land, mixed the ocean's nutrients to support marine productivity, and shaped the calendar systems that organized human civilization. It has provided the stable face in the night sky that guided navigation, inspired art, and anchored the identity of every human society in history. And it has done all of this by simply being there, by having the mass it has, at the distance it occupies, in the gravitational relationship it maintains with Earth. It did not try, it was not designed, it simply exists. And its existence changed everything. Imagine the night sky without the moon. Not the night sky on a new moon when the moon is simply below the horizon or in its dark phase. Imagine a sky with no moon at all ever. A sky where the night is lit only by stars and the faint band of the Milky Way. There would be no monthly cycle of brightening and darkening nights. No dramatic shadows cast by moonlight. No tidal rhythm on the shore beyond the much weaker solar tide. No reliable calendar built on the recurring phases of a nearby world. The night sky would be more star-filled without the moon's glow washing out the faintest stars. But the night would also be profoundly emptier. The sky we have, with a large nearby moon cycling through its phases on a regular schedule, is not the default condition for a rocky planet. It is a specific outcome of a specific event. We have it because the R happened to hit at the right angle 4.5 billion years ago. Other worlds do not have it. We do, and the night sky we take for granted is, in the cosmic ledger, something borrowed. 1 billion years from now, the night sky will be recognizable. The moon will still be there, cycling through its phases, still the most prominent object in the night sky after the sun. The constellations will be different, because the stars themselves are moving, and their positions will have shifted completely. But the moon will be present, slightly smaller in apparent angular size, its tide slightly weaker, the day slightly longer than now by approximately 40 minutes. The axial tilt will still be substantially stable. Whatever beings inhabit Earth in 1 billion years, if any do, will look up at a moon recognizably the moon we know, slightly more distant, but still turning its face toward them, still falling endlessly around this planet as it has done since before the first living cell divided in the warm chemistry of an ancient shallow sea. The eclipse window will have closed or be nearly so. Total solar eclipses will be a thing that happened, not a thing that happens, but the moon itself will still be there, still leaving, still almost here. If any civilization, human or otherwise, survives on Earth for the next 500 million years, that civilization will witness something no human alive today will ever see: the end of total solar eclipses. Imagine standing on a shore and watching what appears to be a total eclipse approaching, the moon moving in front of the sun, the sky darkening, the stars beginning to appear at midday, the corona visible at the sun's edge, the temperature dropping, and then seeing a ring of sunlight appear around the moon's disk. The moon is no longer quite large enough to cover the sun completely. The sky darkens, but not to the deep totality. The shadow of complete coverage will never reach Earth again. That moment, the first annular eclipse in a world that once had total eclipses, will be a measurable milestone in the history of the solar system, a record of the slow departure that has been underway since the moon first formed. Physics will not announce it. No alarm will sound. It will be nothing more than a calculation completing itself, but it will also be a kind of ending that the universe has been quietly working toward for billions of years. The moon has been humanity's most reliable clock. Before mechanical timekeeping, before the sundial, before the hourglass, before the atomic clock, the moon's monthly cycle was one of the most dependable rhythms available to human observation. The interval from new moon to new moon, approximately 29.5 days, is consistent enough to serve as a calendar unit across thousands of years and dozens of independent civilizations. The Babylonians used it, the Maya used it, the ancient Chinese used it, the Islamic world uses it today. The very word month derives from the same root as the word moon. The concept of a month, which organizes so much of modern life from bills to birthdays to academic semesters, is a memory of the moon written into the calendar. As the moon recedes, the synodic month will gradually lengthen because the moon's orbital period increases as its orbit expands. The change is imperceptibly slow by human standards, but the same mathematics that predicts the moon's orbital expansion predicts that the month was shorter in the past and will be longer in the future. The moon's clock is running slow. Gather everything described so far and hold it together in your mind for a moment. A moon formed from the debris of a catastrophic collision, impossibly close at first, gradually receding for 4.5 billion years, simultaneously slowing Earth's rotation and holding its axis stable, and driving the tides that shape the oceans and the intertidal zone, and possibly the first self-replicating chemistry. A moon that has been the most consistent feature in the sky of every living creature that ever evolved well enough to look up. A moon that provided the most precise large-distance measurement in the history of science, bouncing photons off corner-cube prisms left by the last humans ever to walk on another world. A moon that is moving away at 3.8 centimeters per year, imperceptibly by human senses, inevitably by the laws of physics. A moon that created total solar eclipses as a temporary gift to a planet that would not exist to appreciate them, were it not for the same collision that created the moon. This is the story. This is what 3.8 centimeters per year actually means. There is a particular kind of beauty in the fact that the moon's recession is not a malfunction. It is not a disaster in progress. It is not the universe failing to sustain something that should be sustained. It is physics operating exactly as it must, transferring angular momentum from where it was deposited by a collision 4.5 billion years ago to where the laws of mechanics require it to go. The moon is not running away. It is completing a process. The same process that is carrying the moon to a slightly higher orbit every year is the process that once carried a debris disk of vaporized rock and metal into orbit around the young Earth, where it accreted into a moon. The moon's outward journey is the continuation of its formation. The moon is still becoming what it will ultimately be, and what it will ultimately be is slightly farther away, slightly smaller in the sky, slightly less dominant over the tides, not absent, not gone, just further along the trajectory that began with the most consequential collision in Earth's 4 billion year history. What does it mean to live on a planet where the conditions for your existence required a catastrophic collision 4.5 billion years ago? A perfectly tuned debris disk. A moon that formed at exactly the right distance to stabilize your planet's axial tilt and drive the tides that concentrated the molecules of early life, and then stayed close enough for long enough that the entire arc of biological evolution from the first cell to the last heartbeat of complex life was possible. It means you are here because physics was patient and the geometry was right. Not because it was designed to be right, not because anything wanted the outcome, but because the enormous number of rocky planets that form in the universe includes, through probability alone, some that get the collision angle right, some that accrete the right moon, some that develop the right tidal system, some that maintain the right axial tilt long enough for complexity to emerge. You are on one of those planets. You are the outcome of that particular run of physics. This is not a comfortable thought. It is an honest one. The stability of Earth's climate over the past several hundred million years is the background against which all complex life has evolved. The Cambrian explosion, the rapid diversification of most animal body plans roughly 539 million years ago, happened against a backdrop of a planet whose axial tilt was within a few degrees of its current value, whose day was only slightly shorter than today's, whose moon was only slightly closer. The subsequent 500 million years of evolution, from the first fish with limbs hauling themselves onto Devonian mudflats to the emergence of mammals after the end Cretaceous mass extinction to the development of the human brain, all occurred within a climate system fundamentally stabilized by the moon. The ice ages came and went, sea levels rose and fell, continents drifted, extinctions occurred. But through all of it, Earth's axis did not wander chaotically. The seasons came and went in their cycle, the tides rose and fell in their rhythm. The moon kept the whole system within the bounds of what complex life can tolerate. It has never stopped. The moon's recession ultimately means that the conditions Earth has enjoyed for the past 500 million years are not permanent. They are temporary on the timescale of the universe. The stability of 23.5 degrees of axial tilt, the strength of the tides, the regularity of total solar eclipses, the 24-hour day, all of these are features of a specific moment in Earth's history. Before this moment, the moon was closer, the tides stronger, the days shorter. After this moment, the moon will be farther, the tides weaker, the days longer. The window in which these conditions exist, the window in which complex life as we know it flourishes under a stable moon and a stable sun, is not a permanent address. It is a temporary residence. We are living in it now. Every other species on Earth is living in it now. Everything that has ever lived on this planet has lived in some version of this window. The window is still open, the moon is still here, and in that fact, in that present tense reality, there is something that deserves to be recognized as extraordinary. There are people alive today who have traveled thousands of miles to stand in the path of a total solar eclipse and experience those 2 to 7 minutes of totality, of the shadow rushing across the landscape, the corona blazing in the suddenly darkened sky, the planets appearing at midday, the temperature dropping, the birds going quiet. Those people understand something that most of humanity does not, that a total solar eclipse is not just a spectacle. It is a reminder of an extraordinary coincidence that science has exploited to discover the outer atmosphere of our star, to confirm Einstein's general relativity, to probe the sun's magnetic field in ways that direct sunlight makes impossible. This coincidence exists right now. It has existed for tens of millions of years. It will exist for hundreds of millions of years more. But it has always been on loan. It was always temporary. The 3.8 centimeters per year is the rate at which the universe is paying down that loan, 1 centimeter at a time, 1 year at a time, without urgency, without drama, without even the slightest awareness that anything precious is being spent. The universe does not notice. This is important to understand. The tidal friction operating between Earth and Moon, the angular momentum transfer, the recession of 3.8 centimeters per year, the lengthening of the day, the weakening of the tides, all of this is occurring within a single, unremarkable solar system, around an ordinary main sequence star, in the outer arm of one of roughly 2 trillion galaxies in the observable universe. The universe contains processes that make the Earth-Moon system's billion-year evolution look instantaneous. Supermassive black holes consuming material at billions of solar masses per year, stars forming and dying in their millions, galaxies merging and dispersing over timescales that make the entire history of Earth look like a brief flicker. The patient work of tidal friction, 3.8 centimeters per year, is not noticed at any cosmic scale, and yet locally it has produced everything. The universe's complete indifference to the small things it creates is, in a strange way, the very condition that allows those small things to persist long enough to become extraordinary. You are on a planet that is in an ongoing transaction with its moon. Earth gives the moon orbital energy. The moon gives Earth its stable seasons and its tidal rhythm. The exchange rate is 3.8 centimeters of orbital altitude per year, 1.8 milliseconds of day length per year. These numbers are small, they are not nothing. They are the continuously updated account balance of a physical relationship that has been running without interruption for 4.5 billion years. The moon is not going away, not in your lifetime, not in the lifetime of your civilization, unless that civilization achieves something of truly extraordinary duration. The moon will be in the sky tonight. It will be there for every generation that follows ours, slightly farther, slightly smaller in apparent size, but present, constant in its phases, still ruling the tides, still stabilizing the tilt. The recession is real, the implications are vast, but the moon, right now, tonight, is there, 384,000 kilometers overhead, moving away, still here, both things equally true. Phase 7 begins here, at the close. Go outside tonight and find the moon. Find it in whatever phase it is in and look at it for a moment longer than you normally would. Look at the Maria, the dark flat plains of ancient lava that early Apollo astronauts could see growing larger in their windows on the final approach. Look at the bright highland regions where the ancient crust survived the late heavy bombardment. Look at the Terminator, the line between the sunlit and shadowed portions of the lunar disk, where low-angle illumination throws craters and mountain ranges into sharp relief and makes the moon look like a world, which it is. You're looking at something that has been in this sky for 4.5 billion years, something that formed from the wreckage of a catastrophic collision before the first single-celled organism ever existed on Earth. Something that has been moving away from you at 3.8 centimeters per year for the entire history of life. And it is there right now, tonight, overhead, moving away, present. Somewhere in human history, the first person to understand that the moon was not a lamp in the sky, but an object in space, must have felt a particular kind of vertigo. The shift from moon as decoration to moon as world is not a small cognitive step. It requires the mind to extend the familiar, the solid ground beneath your feet, across 384,000 kilometers of vacuum to a world of craters and dust with no air, no weather, and no life. That shift happened gradually, through centuries of naked eye astronomy, telescopic observation, and finally the orbital mechanics that allowed us to plan trajectories and send people there. The people who first understood the moon was a world, and then the people who proved it by going there, and now the people who bounced lasers off the retroreflectors they left behind, all are participants in the same long human project of understanding where we are and what the things around us actually are. 3.8 centimeters per year, measured, understood. Still, even now, slightly astonishing. The moon will be full in a few weeks, or in a few days, or perhaps it is full tonight. When it rises, it will be orange near the horizon, shifted in colour by the thickness of atmosphere it must shine through to reach your eyes, and then it will climb through gold to white as it rises higher. It will cast shadows on the ground. It will turn the sea a pale silver and make the waves visible in the dark. It will reflect sunlight that left the sun 8 minutes ago, bounced off the moon 2 seconds later, and arrived at your eyes in the present moment. That light is ancient light from a star 4.5 billion years old, reflected by a world that has been receding from Earth for 4.5 billion years, arriving at a brain that evolved under the influence of the same moon for hundreds of thousands of years. The light takes 2 seconds from the moon. The story took 4.5 billion years. And on an evening when the full moon rises clear and bright above the horizon, both of those facts are equally true. What makes Earth remarkable is not the drama of its early history. It is the stability. Other rocky planets have dramatic histories. Venus with its runaway greenhouse, Mars with its lost ocean and vanished magnetic field, Mercury with its massive iron core. Earth's drama, the Theia impact, the late heavy bombardment, the snowball Earth events, the great mass extinctions, all occurred against a backdrop of the continuous stabilizing forces, the magnetic field, the carbon silicate cycle and the moon. The moon's stabilizing role is not its most spectacular attribute. It does not explode. It does not change color. It does not send visible signals of its influence. It simply orbits, slowly receding, quietly holding the axial tilt within bounds, quietly driving the tides, quietly maintaining the system within the parameters that allow complex life to persist. The most important things are often the quiet ones, the things you only notice when they are gone. We will not notice the moon's influence in the day it diminishes. We would notice its absence. That absence for now is not something we need to contemplate. The moon is present, still working, still here. Right now, the moon is at the distance it needs to be to stabilize Earth's axial tilt. Right now, the tides are at the strength they need to be to maintain the intertidal zone and the oceanic mixing that supports marine life. Right now, the moon is close enough that total solar eclipses are still possible, that astronomers can still study the corona at every total eclipse, that Einstein's general relativity can still be confirmed against the deflection of starlight during totality. Right now, the day is 24 hours long, the right duration for the atmospheric and oceanic circulation patterns that distribute heat around the planet and maintain the temperature ranges in which complex life survives. All of these conditions are products of where the moon is at this specific moment in Earth's history. They are not permanent. They are a configuration, not a promise, but they are here now, and being here now means something. It means we are alive inside the window that the entire arc of complex life has unfolded within, open, still open. The same impact that will eventually lead to the loss of the moon's stabilizing influence gave us everything we have. Without the Theia impact, no moon. Without the moon, no stable axial tilt, weaker tides, possibly no complex life, possibly no life at all in the form that eventually produced intelligence and inquiry, and the ability to discover that the moon is moving away. The very thing that is slowly receding from the sky is the thing that made it possible for eyes to develop that can look at the sky. The process that is depleting the moon's tidal grip on Earth is the same process that created the intertidal zone where early life learned to breathe air. The recession is not the cancellation of a gift. It is the continuation of a story that began with violence and has been for 4.5 billion years, producing extraordinary things. The Theia impact is still writing this story. The moon's recession is still a chapter in it. And the chapter we inhabit right now, the chapter of complex life and curiosity and measurement and understanding, is among the finest chapters the story has produced. 3.8 centimeters per year. This year, the moon moved 3.8 centimeters further from Earth than it was last year. Next year, it will move 3.8 centimeters more. The year after that, the same. You will not feel it. You will not see it. No instrument you own will detect it. The tides will rise and fall on the same schedule. The moon will cycle through its phases on the same approximately 29.5-day period. The night sky will look identical, but the measurement is real. The retroreflectors on the moon are bouncing laser pulses back right now, from observatories in New Mexico and in France and in Italy, and the data is confirming the same number that lunar laser ranging has been confirming for 50 years, 3.8 centimeters. It tells you something about the nature of reality that no amount of comfortable certainty can undo. The world you take for granted is not standing still. It is never standing still. It is always, in every moment, becoming something slightly different from what it was. The moon is the measure of that truth. Somewhere in the future, a human being or something that was once human will witness the last total solar eclipse. They will not know it is the last one. There will be no announcement. Physics does not announce its milestones. The moon will move in front of the sun as it has done countless times before. The sky will darken, the corona will blaze, the temperature will drop, and then the moon will pass and the sun will return. And the next time the geometry aligns, the moon will be slightly too small to cover the sun completely, and what was once a total eclipse will be an annular eclipse. The change from total to annular is as imperceptible year to year as the change from 24 hours to 24 hours and 1.8 milliseconds, and yet the cumulative effect over hundreds of millions of years is the closing of a window that has been opened since the moon formed close enough to Earth that its apparent size exceeded the sun's. The last total eclipse will come and go. No one will know it was the last one. Physics will simply move on. Pull back far enough, and what you see is a solar system in the middle of its history, a star burning through its hydrogen, a planet in the ongoing aftermath of a catastrophic early collision, a moon slowly writing its departure in the geological record. A brief window of complex life unfolding within this specific configuration of masses and distances and rotational states. Pull back farther, and the solar system is a small point in one arm of a galaxy containing 400 billion stars. Pull back farther still, and the galaxy is one of 2 trillion in the observable universe. At that scale, the 3.8 centimeters per year is nothing. The entire history of Earth is nothing. The window of complex life is less than a rounding error in the age of the universe. But pull back into this specific moment, this specific planet, this specific relationship between a world and its moon, and the 3.8 centimeters per year is everything. It is the measure of a relationship in progress. A relationship that has produced through 4.5 billion years of slow and patient work the capacity to measure itself. The moon is moving away. It has always been moving away. When the first cells were dividing in the shallow Archean Sea, the moon was moving away. When the first fish crawled onto land in the Devonian, the moon was moving away. When the first mammals opened their eyes on a dark night, the moon was moving away. When the first human ancestor looked up and wondered, the moon was moving away. When the first astronomer calculated its orbit and named its motions and understood the mathematics of its path, the moon was moving away. When Neil Armstrong placed the retroreflector on the lunar surface in 1969, the moon was moving away. It is moving away right now as you listen to this. 3.8 centimeters per year, not faster than that, not slower, just that number, steady and precise, writing the future of this planet in small increments that add up over billions of years to everything. The moon is still here. It will be here tomorrow, but it is going. It is always going. It has never, not for a single moment in 4.5 billion years, been standing still. There is something deeply human about the relationship with the moon. Not in the sense that the moon was made for us, which it was not, but in the sense that we have always organized our understanding of time, place, and beauty around this object. The farmers who planted by the moon's cycle, the sailors who navigated by its light, the scientists who bounced lasers off its surface, the poets who wrote of it through 100 generations, the lovers who stood beneath it on innumerable quiet evenings. All were in relationship with a world that was always moving away from them. 3.8 centimeters per year is the rate of the moon's departure. It is also, in a sense, the rate at which everything departs. Every relationship, every moment, every configuration of the world that produced something beautiful or important or true is, in some sense, always moving away. The moon does not make this poignant. The moon makes it visible. In the measured distance, in the precise number, in the laser returning from the retroreflector with its 2-second journey encoded in its arrival time, the departure is made legible. The leaving is given a number. Breathe. The moon is there. It has been there every night of every life that has ever been lived on this planet. It has been the clock, the calendar, the compass, and the companion. It has held the tilt steady and driven the tides and lit the path through 100,000 years of human nights. It is going. It has always been going. And knowing that it is going does not diminish it. Knowing the physics of a beautiful thing does not make the thing less beautiful. It makes the beauty legible, gives it context, places it in the long story it has always been part of. You're here because 4.5 billion years ago, a planet called Theia struck the young Earth at exactly the right angle. The moon that formed from that collision has been your planet's companion ever since. Tonight it is 384,000 kilometers overhead. It will be 3.8 centimeters farther away by this time next year. And tonight, in this moment, it is as close as it will ever be again. Look up.